Hello, I'm charging my 8S sodium ion battery with this power supply. It's a buck boost charger. It's set to, well, it's set to 1 amp, I think, also 30 volts. Now this battery is 32 volts at the top of charge. Well, that's if you take it to 4 volts. I may not take it to 4 volts. So I'm taking it to, I think, 3.75 volts per cell. So the battery is up to 30 volts. You can see that on the two voltage monitors. Can't see it very well, can you? But 15 volts on 4 of the cells, 15 volts on the other 4 cells. Now these little Heltec voltage indicators, you can only get them in 4 cells. So for this 8 cell pack, I've had to use 2 of these little displays. I'll get in a bit closer. But before I do, I just wanted to say, yeah, that's now voltage limiting at 30 volts. And because these are quite saturated, it's now down to just 50 milliamps. So here's a closer look at these 2 displays. You can see the individual cell voltages, but I'm not 100% sure that these are completely accurate, because the balancers should be, I mean, they're very low power balancers, but they should be bringing the cells into balance. And I keep seeing these 2 cells, which I think actually are the most positive cells, are significantly higher. Well, I say significantly, I mean, actually, I'm looking at the 3rd digit. It'd be more sense, actually, if these were just 2 decimal places, because you do get very distracted by this 3rd digit. I mean, they're all 3.75, but this is 3.754 or 3, and this is now 3.760. Now, there's a problem with these displays. They show the lowest cell in the pack, the most negative cell in the pack, at the top. So S1 is cell 1, but I laid these 2 displays out so that this display shows the most negative cells and this shows the most positive. So now they're in a total mess, because I think cell 0 is here, and then cell 1, 2, 3, 4, 5, 6, 7. So this is the most positive cell. Actually, this could be easily solved by simply pulling these 2 plugs out, or even lifting these things off their hangers. I've just put them on these hooks because I couldn't find any screws small enough to fit through these holes. So let's see if I can do this on camera, because it'll make more sense if these are in a linear progression from one end of the pack to the other. This will be the most negative end at the top, because you can't rearrange these 4, it just won't have it. You can kind of see how it works, because the black wire is at the top, and that's the most negative cell. The red wire is at the bottom, and that's the most positive cell. So I'm going to switch these around. There shouldn't be too much difficulty with that. Oh, I just put my hand in the little fan on my power supply and got a little nip and wondered what it was. But let's plug these round so that they're in the correct sequence, so I can see what I'm doing. I can't get to this very easily. And of course, all the time I'm being careful not to short anything out which shouldn't be shorted out. Why couldn't that go in? Okay, so now most negative cell is at the top. That's cell 1, 2, 3, 4, and these will be cells 5, 6, 7, and 8. And it's these 2 at the bottom here, the most positive cells, which give this sort of unusually high reading. But anyway, let's move on to these 3 balancers. Now these boards are very tiny, and there's no mounting point. There's no hole. Well, there is a hole, but it's very tiny, and it would be very impractical to use as a mounting point. But I'll come back to that later. There's a 3S balancer, a 4S balancer, and a 3S balancer. And the way this works, oh, I need to just zoom out a bit. The 3S balancer, oh, I can't remember which one's which. Yeah, this one, I think, is doing the bottom 3 cells here. So these 3 cells at the bottom, which are the most positive, I think. Then the 4S balancer is doing these top 4 cells. If I just raise the camera a bit, you can see that the 4 cells at the top are being done by the 4S balancer, and then this 3S balancer is doing the bottom 3 cells again, but the ones around the back. But what you can see is that the 3S balancer is doing the bottom 3 cells, the 4S balancer is doing the top 4 cells. So this cell here and its counterpart around the back are on both balancers, because you have to create this overlap so that it can take charge from this cell and move it to these, and also take charge from this cell and move it to these, or vice versa. One thing I've noticed is that before I swapped these around, they were reading almost exactly the same pack voltage, which I think was, I don't know, 15 point something, but they were the same. Now that I've swapped them around, they're not the same, which is interesting, because the point is the balancers work slowly, but over a long time, like overnight, because they're on all the time, they should balance the cells between them. But of course they balance them at a slightly different voltage. I have, since the night, put this power supply on and raised the voltage to 30 volts, and we're now down to a very low current of 50 milliamps. So they're good and saturated at that 30 volts. But yeah, that's interesting that that's changed. Why are these now mismatched? Now, something you may have noticed, these LEDs are very different brightnesses. The 3S LED is quite dim. The LED on the 4S is much brighter. Now, of course, initially the thought is, oh, well, this is spanning 4 cells, so it's getting a higher voltage into that LED. I don't actually know where that LED is wired, whether it's just wired across one cell or whether it's wired across the whole pack. There's another reason why this one is so much brighter, because it is really massively brighter than the LEDs on the 3S. And for that, we'll take a closer look at those balancers. So to compare them, I will need a 4S balancer, and that's a 3S balancer in there, isn't it? I've also got an 8S balancer, which I've shown before, but it's a sort of oddity because it's actually 2 balancers with this overlap. But anyway, we'll worry about that another time. Now, before I get close up on these things, what would you say is a suitable current limiting resistor for a green LED? Now, I know it depends on what voltage you're going to put across, what voltage you're putting the LED and its series resistor across, but just ballpark. I mean, in the old days, I always used to think of sort of 470 ohms was a good current limiting resistor, with 1K being a bit high. Well, check out the resistors on these things. So why is the LED on the 4S balancer so much brighter than the one on the 3S balancer? Well, there's the series resistor for the LED, 104. Now, if I remember correctly, that is 100K. It is, isn't it? 100 and then 3 more zeros. So 100K ohms is the series resistor for this. And these green LEDs are so efficient these days that you can get a reasonable amount of brightness even with an extremely high value series resistor, 104. But the one on here is even more crazy. It's 105. So if you were sort of saying, oh, series resistors for LEDs are typically in the, I don't know, 220 ohms up to, I can't get that focused, but yeah, 105. That's 1 megohm. They're using a 1 megohm series resistor for current limiting an LED. I would never have thought to use a 1 megohm resistor. But anyway, why are they using a 1 megohm on this 3S balancer and a 100K on the 4S balancer? I must admit, I'm very tempted, and you can see I've snapped off the little plastic leg of that connector there. Very tempted to desolder the 104 on this because it's too low a value, and stick in a 1 megohm resistor on the 4S balancer. So that explains why this LED on the 4S balancer is so much brighter, because it's got a 100k ohm resistor, where these LEDs have got 1 meg ohm in series with them. I still can't remember whether they're across the entire 3 cells in the case of this and 4 cells in the case of this, or whether they actually are wired across one cell. Well, let's have a quick look, shall we? Yeah, I think you can see, or I hope you can see, the LED has a little via there, and the resistor has a via up there, but it's actually connected to this MOSFET. I think that might be a source pin. But this via here next to the LED, if we flip it over, it runs along this track at the top and goes out to this point here, which is 0 volts. Where that tiny little hole is, now you can see that that is the only hole on this PCB, so there's no other way of mounting this other than that hole. And if you found a piece of wire small enough, whoops, to fit through that hole, it wouldn't be very strong, so it wouldn't really make a very good mounting point, would it? But yeah, so it looks like the LED wire goes to ground, and then this resistor is connected to, well, this MOSFET here. Oh, what's that whisker hanging off the capacitor there? That's horrible, isn't it? This MOSFET here, which is, oh, I think connected to this point. So I think it's the higher voltage. So it does look like the LED is strapped across all of the cells, in this case 3, and then the one on the 4S balancer is strapped across, it'll be a similar arrangement, is strapped across 4 cells, but that is only a 3:4 ratio. The brightness of the LEDs is much more relevant to this 10:1 ratio of the 1 meg ohm resistor and the 100k resistor. Right, now let's take a look at one of these Heltec 4S voltage displays. So I'll disconnect the connector. I'll just show how it works. There's a little DIL switch on the back here. You can see the 4 solder points here. One of the switches, it's a 2-switch pack. One of the switches inverts the display, so it works upside down. The other one decides whether or not these displays turn off after 15 seconds. I've set it so they don't turn off after 15 seconds, but you can manually turn them off and they will stay off permanently, and manually in this mode turn them back on. In the other mode, if you slide that very top switch, they always turn off after 15 seconds. But let's get one of these down on the bench. So here it is, made, as I say, by Heltec BMS. There's the DIL switch, so if this switch number 2 is on, then the display stays on permanently, but you do have the ability to switch it off with that switch. There are no other real controls. The switch number 1 is the invert. Like I say, it just rotates the display 180 degrees. So let's just have a look at what's on here. Okay, so on the back we've got the LCD connector down onto the board. This chip is actually a BYD chip, the manufacturer of batteries and electric cars, but it might just be an ST32 type of architecture. I don't know much about BYD microcontrollers. I assume it's a microcontroller. Yes, I think it probably is, because we probably got some programming header up here. Now this chip here says Lindsay, Linsi, and I'll see if I can get the number so that it's visible. So it's either an NW3L2H or it's an LS76920. I don't think you'll find anything on it. Well, I didn't the last time I looked. But it looks to me like the cell voltages all appear here, where these capacitors and, I don't know, bypass diodes or some sort of diode there all come into this chip. So I think this is some sort of battery monitor, battery voltage monitor chip. It looks like there may be a buck converter here, possibly to yeah, that might be the controller chip there. TH or 1HWG, something like that, to provide a voltage to run these controller chips, because they're not going to want 30 volts or 15 volts across there in my case. And then possibly some regulators down here. But yeah, I think this chip is doing the voltage measuring of the different cells, and then this is a microcontroller which probably has built-in LCD drive capability. But that's all that's on here. Now you can see that the holes, I think they were 2mm or possibly a bit more than that, but I've drilled them out to 2.5mm. But because they're so close to the edge of the board, you can't really drill them out any more than that, otherwise these points just will get so weak. And I don't really have a very good selection of screws of 2.5mm. I've also drilled that one out. That's slightly bigger than this one down here. But yeah, they're very close to the edge, so you're limited in how much you can drill these out, which is why I'm hanging it on hooks rather than using screws to screw it to my wooden backboard. But they do make voltage monitoring easier than the alternative which I used previously, which was to take apart little single cell battery voltage testers which had the nice monochrome LCD. The trouble with these is they do use quite a bit of power on this color TFT, and they're not really making very good use of the colors, are they? A monochrome TFT would have been perfectly good. Right, let's put this on here and bring it around like so. And now let's plug in this wire. Black is at the top. Yeah. Can't see what I'm doing because I can't really see in 3D at the moment. But yeah, I think these are quite a nice option for looking at that. I mean, it's not ideal for an 8-cell pack because you split the pack voltage into two amounts, so it's 15 volts plus 15 volts. This is a 30 volt pack. In fact, you can just see on here that these are 30 watt hours and 3 volts, so they're 10 amp hour cells. So the whole pack with 8 cells in series is also 10 amp hours, but it's 8 times 3, it's a 24, so it's 240 watt hours. It's a quarter of a kilowatt hour. So what else have we got on this battery? At the moment, I decided that I wanted to double up the pos and neg connectors here, just to make this more versatile, because I've got one set of connectors coming from my charger power supply, which is going in on these 2 points, and then these 2 connectors are going over to my, oh, I don't think you've seen this, my new parallel banana sockets on a piece of wood, but also 2 of these bulb sockets, which I've actually put in series, and these are 24 volt bulbs. Because this battery pack is 32 volts potentially at the top, I thought that's too much for 24 volt bulbs, so I thought if I go for 48 volt bulbs, and I also bought some more of these 21 watt brake light bulbs. These are also 24 volt, I think it says on there. Yeah, these are Philips. I actually bought them from the Philips store on AliExpress. Why is there a Philips store on AliExpress? Bit strange. But yeah, so I can take out the 5 watt bulbs and put in the 21 watt bulbs. Of course, you wouldn't do it like that, would you? Because this would act pretty much as a piece of wire, and this would take the whole 30 volts, so that wouldn't be a good idea. Don't mix and match bulbs in series. So the next thing I want to add to this battery is a coulometer, and I have actually 3 coulometers. Well, I've only got 2 here. Yes, I have this TK15 coulometer with a really nice slimline display, and this sampler module, which is a 50 amp sampler module made by Byway, and it's identical to the sampler module on this other unit, which is called a TY23, which is not as good because it's only got one numerical field displayed on the display. This has multiple fields. So I'm going to have to make a video of these things. The other display here is an H56C coulometer, and this one actually has a non-invasive, well, they say non-invasive, you pass the wire through this coil, but it has very crude current measurement. It only shows it to 1 decimal place, whereas these two show current to 3 decimal places. But yeah, you know, you don't have to interrupt the circuit to pass it through a shunt, but you do have to interrupt it because you've got to pass it through that hole, and it doesn't have an opening clamp type current sensor. So I'm not sure whether that's a huge advantage having that coil, but yeah, I'll make a video on these 3 coulometers. I think I'm going to go for the TK15, but I'll explain why in my coulometer video. So that's an update on the build of this 8S sodium ion battery with these balancers. These, incidentally, I meant to say, are just velcroed onto this bar because of that business of the fact that the finger in the fan again. They don't have mounting holes, or not that I could work out a system for mounting them, so I've just stuck them on Velcro, which is not ideal, but then these are not ideal either because they kind of swing on these hooks, but whatever. So this battery will be going in the shed when it's got its coulometer, and it's going to be for shed lighting. Ooh, yes, I need to talk about the lighting, don't I? Why has that gone up to 62 milliamps? Oh, it's probably these things, isn't it? Yeah, if I turn these off, that will probably... Oh, yeah, that's gone right down. That's interesting. So 38 milliamps. So these probably draw about 30 milliamps between them. And if they're on, that rises to 60 milliamps, which is hardly surprising because you've got the backlight LED. Yeah, interesting. Now in the shed, I have predominantly got these strip lights, and they're just multiples of these little circuits, which are 3 white LEDs in series and a series resistor which says 390, and I once erroneously called that 390 ohms. Of course it isn't, it's 39 ohms. So 39 ohms, 3 white LEDs in series, and then that cluster is just repeated paralleled up all the way down the strip, and at one end you've just got a couple of wires coming out to hook these lights up to your voltage source. Now the problem with these is they're not very flexible in terms of the variability of voltage. They like 12 volts. If you go much below that, they get very dim. If you go much above that, they get extremely bright and very hot. So you really do need to stick at 12 volts. And that will be a problem if I'm using these sodium ion cells. With 8 of these in series, the maximum voltage, if you take them up to 4 volts each, will be 32 volts. I might top out at, say, 30 volts, but that's certainly not any good for these LED strips. The minimum voltage practically will be about 2 volts per cell, but even that with 8 cells in series is 16 volts, well above what these lamp strips can take. So the only way these are going to work in conjunction with this 8S sodium ion battery is to put a buck converter after the battery to take the, well, anywhere between 16 and 32 volts down to 12 volts and run the lights off that buck converter. But I also have these things. Some of them are have a little white plastic, translucent plastic front on them. 2 wires coming out. Some of them are bare strips like this. So you can see the individual LEDs under this sort of yellow jelly type substance. But under this little black area here is a buck converter. And in fact, you can see on this one it says 12 to 85 volts. So the sodium ion battery with its 16 to 32 volt voltage range would be fine connected directly to these things. In fact, I'll do that in a minute. because these can take up to, well, maybe not quite 85 volts. I'm not sure I'd push them right to the top, but certainly a voltage well above the 32 volts on the sodium ion battery pack. So I can put these in the shed. Here's a different one that's not as long and thin. These are better because they fit the sort of wooden beams that run across the roof of my shed better. But they've all got this integrated buck converter and can take, I don't know, 75, 80 volts on the input. Yeah, these can be connected directly to this sodium ion battery, and as it varies between 16 volts and 32 volts, these won't change in brightness and they'll work fine. Right, what's the best way to do this? Can I poke these wires down the holes in these banana plugs? Got to get the polarity right, haven't I? It's going to be very hit and miss as to whether I make a good connection, but let's give it a try. Oh, a little bit of a click there, but yeah, that's one of these things lit up with, oh well, 30 volts going into it, and there's a little on-off switch there. So that's the current state of play with this 8S sodium ion pack with balancers and cell voltage monitors. Coulometer coming next, but I want to do the Coulometer comparison video first. But that's it for this video, so cheerio.